So we are continuing with chapter 16. We just finished the delta G equals negative. Delta G equals delta G standard minus RT ln of Q. Now we're going to relate Q to K. Okay. So remember our initial equation that we had before, delta G equals delta G standard minus RT times the natural log of Q. This reaction shows the pressure dependence of delta G, okay? Because Q will be the product pressures over the reactant pressures. If we're at equilibrium, delta G here is equal to 0. And then at equilibrium, Q becomes K, because remember, before equilibrium, Q is the initial sets of conditions. But at equilibrium, Q becomes K. It's the same formula, different sets of concentrations or pressures. All right? So then in my formula, I can put a 0 here, and then I can change Q to K and solve for delta G standard. And now I have delta G standard equals negative RT times the natural log of K. This is an extremely important reaction because now we have the equilibrium dependence of delta G and we can predict the shift in equilibrium. Okay, so remember that K, or Q even, is equal to the pressure products over the pressure reactants. Okay, so when delta G is equal to 0, K is equal to 1. The natural log of 1 is 0, right? So when delta G is 0, K is equal to 1, and these two concentrations here are the same, all right? However, when delta G is less than 0, in order to get a negative delta G, I have to have a positive K, a very big K, okay? Because the natural log of that K has to be positive. So in order for the natural log of K to be positive, so that this entire thing can be negative, K must be very, very large, or larger, much larger than 1. If K is much larger than 1, that means I have a small value on the denominator. A small reactant, remember we have reactants making products, right? So if I have a small reactant concentration, the reaction is going to shift to the right to make more products. Now let's do the opposite. If I have a positive delta G is greater than 0, that means this number here has to be positive. I have a negative here, so whatever this is has to be negative in order to equal a positive. The only way the natural log of K can be negative is if its K is a very, very small value. Okay? And for K to be a small value, my reactant concentration has to be very high. Okay? So the bottom number here is a big number for K to be small. And if that number is a big number and I have a high reactant concentration, it's going to shift, the equilibrium will shift to the left. So now we're going to estimate equilibrium constant and the position of the equilibrium for this reaction at 25 degrees Celsius. So here is my reaction, and I am solving for K. Alright, I know R, that's 8.314. I know temperature, which is 25 plus 273, which is 298 Kelvin, which is standard temperature. Okay, so since I'm at standard temperature, I can use Appendix 4 to calculate the standard delta G. Use the values from Appendix 4. When you do that, you should get the delta G standard is equal to negative 1.48 times 10 to the 6th. And I'm going to put it in joules, okay, because R is in joules per mole Kelvin, so I have to have it in joules, okay? So make sure you do delta G using the back of your book in order to get this number before you continue. So once you get that, you have negative 1.48 times 10 to the 6 joules is equal to 8.314 times 298 times the natural log of K. Alright? So when you do everything move everything to the other side, you will get that 597.4, sorry, is equal to the natural log of K. and you take the inverse natural log. And when you take the inverse natural log in your calculator, it's going to have an e, that's the mathematical function, to the 5. This is not 1 times 10, okay? So it's a math function, 597.4 is equal to k. That's the inverse natural log. When you do that in your calculator, it doesn't matter what the number is. What you see is that's a big number, big K. Remember, if there's a large K, there's a large product concentration. So the equilibrium lies far to the right, and the reaction is favorable. The equilibrium lies to the right if K is big. Now let's do the same thing for this reaction. Since this time we're not at 25 degrees Celsius, we cannot use Appendix 4. But this is still my reaction. Except that I can't use Appendix 4 to calculate delta G directly, okay? But I can use these values, delta H and delta S, from Appendix 4. And then use delta G equals delta H minus T delta S. Remember, delta S is temperature dependent. This is temperature dependent. So if I'm not at standard conditions, I have to use this way to calculate delta G. Okay. So when you do this in your calculator, and we have done this in example E from a few slides ago, okay? So from a few slides ago, we found that delta G for this reaction is equal to 473,000 joules. So now I have that delta G, 473,000, equals negative R, 8.314, times T, which is 427, plus 273, so that's 700, times the natural log of K, and we're solving for K, okay? So if I move everything over, divide by 8.314, divide by negative 700, and you should get negative 8.12 is equal to the natural log of K. So in your calculator, get the inverse natural log of both sides, and you should get that K is equal to e to the negative 8.12, which is 2.95 times 10 to the negative 4. So that tells me I have a very small K. So K is small. If K is small, then I have more reactants than products, okay, because that bottom number, the denominator, has to be very big. So if that number is very big, then the equilibrium lies to the left. So we're predicting the position of equilibrium. It lies to the left in this case. So it's not making products, it's making more reactants. And that means it's not thermodynamically favorable. And remember when we did Le Chatelier's principle, as for an exothermic reaction, if temperature went up, K went down, because remember how we said for exothermic, K is heat is the product, okay? So we increase heat, we decrease K because the reaction shifts to the left. For endothermic reaction, the opposite is true. As we increase temperature, we increase K, all right? So K depends on temperature. The rate constant K did not. The lowercase k doesn't depend on temperature. But equilibrium K does depend on temperature. So if we put these two reactions together, we can get a linear relationship between K and temperature. So the natural log of K is equal to M, the slope, which is delta H over R, times X, which is the inverse of the temperature, plus, and this is my y-intercept, okay? So now I have a linear relationship between temperature and K. Okay, we've already discussed this, that free energy is the maximum possible useful work. So this is just reiterating that point, and you can read about that in your book on page 824 to 826. This is just information for you about light bulbs, heaters, and watch. Just things that in the past students wanted to know how much energy a joule really was. So if you read through this is just more information about what a joule is and how much energy it actually is, since we've done so many energy reactions. And this is also just more energy from you, how much 1 joule is in your everyday life. Um, so 1 joule is the amount of energy to lift a small apple 1 meter straight up. Okay, so 1 joule is not a lot of energy, but we've been doing reactions that are 300, 400 joules, thousands of joules. Okay, so think about that when you read this. That's the end of chapter 16.